Hi, today we are going to present our progress updates. This is Jung Kang, who is the first presenter today. Here is our contents. This is our topic, task-oriented dialogue system. It has the purpose of helping the user to achieve specific goals, such as restaurant booking. Here we brought an example of the uses of the task-oriented dialogue system. The user's utterance on the left and the system responses on the right. At the end of the conversation, the system generates API call to complete the given task. So given these systems, the suggested problem is that how can a system understand a user's intent and messages while effectively incorporating knowledge about the task. In this paper, they used Bobby dataset for training and testing, which we also used. Bobby is a simulated dialogue data with 1,000 questions each for training and testing. It has 5 end-to-end dialogue learning tasks and has specific domain on restaurant reservation. Also, it breaks down a task-oriented dialogue into several subtasks to verify functional capabilities in the domain. Each subtask are sequential. And here is an overview of the model that we are replicating. As you can see, it is a combination of an encoder and decoder. I will give a brief overview on the structure and further details will be given in our replication section. The following figure is the part of the training dataset of Bobby. The IDs for a given dialog starts at 1 and increase. When the IDs in a file reset back to 1, you can consider the following sentences as a new dialog. When the bot speaks 2 times in a row, the special token silence is used to fill in the missing user utterance. The goal of the task is to predict the bot utterance that can be sentences or API calls. Here is an example of the dialog.
Okay, this is Charlton Ho, and it is an application part. We will briefly discuss some of the terms that will be used in the research. Memory is a set of trainable embedding metrics that map tokens into embeddings. Here, tokens mean words and other knowledge that are used in dialogue. The collection of subject, relation, and object is called knowledge. It is the information that the system needs to know to carry out tasks. For instance, to incorporate the information that the fancy pub is located in London, it can be expressed in this form: the fancy pub, our location, London. First, let's see how dialogue data is represented in this model. As stated in the previous slide, dialogue-like knowledge is treated as a triple. All utterances are split into words and then converted into a triple as seen here. Let's take an example and see how the training of the dialogue system works. This is turn 1. First, user starts the system and fires silence. Then the model is taught to respond, "How may I help you?" as a response. To generate a response for turn 1, insert user's turn 1 utterance into the encoder as input. The statement is split into words. In this case, there is only one word. A triple is generated from the words. The information is the word, the speaker, and the turn number. The triple is increased through the encoder, and the result is inputted into the decoder. The decoder then generates "How may I help you?" end of sentence, which is the response of the statement. The following is for generating a response on turn 2. Statements from user and the system on turn 1 and from user on turn 2 are sent to the encoder in triple forms. Then decoder creates a response that says, "What kind of food would you like?" You can see memory to sequence model consists of an encoder and decoder components. In a nutshell, encoder has a responsibility to encode source input, and decoder decodes encoded input to generate output. Now we will look into each one of components.
Coder consists of memories, which is a set of trainable embedding layers. You can see from C1 to C4 in this figure. The query vector is a reading head over the memories and it begins with 0. A soft attention mechanism developed the query vector. First, as you can see the equations, it get attention P by doing dot product over query and current hop. Then output is weighted sum over the next hop. Finally, it updates the query by residual sum of current query and output. The decoder loads input sequence, which are utterance and knowledge, into its memories. Instead of using zero vector as a query vector, decoder uses GRU to generate it. The decoder produces two distributions as outputs, vocabulary and memory pointer. To generate vocab distribution, the first whole embedded output and query vector are concatenated and folded to a linear layer. The last hop attention is used as a pointer distribution. To train our model, we use the following specification. Operating system is Ubuntu 16.4. CPU is Intel Xeon. For the GPU, Titan XP was used with 512 GB of RAM. With this specification, we trained this model with total 70 iterations in total, and it took 5 minutes per iteration. Okay, training result. The following figure shows dialogue accuracy over the epoch. We got about 62% of dialogue accuracy. However, we found 73% accuracy in the paper. This is because author didn't suggest the best hyperparameter of this model, and we still figured it out. We expect we will find it in the end. We found it is hard to understand codes written by someone else. We decide to rewrite the codes to understand better and deeply. Also for future modification. While implementing, we faced some difficulties to write mathematical equation and logic into the codes. Googling helped a lot. As we said before, we still try to find the best hyperparameter of this model.
Hi, my name is Eugene Zhang, and I will introduce the improvements we're making to this model. We identified two places where we feel we could make significant improvements in the model. The first is in how the model combines embedding triples, and the second is how the model represents temporal information. So for each word in the dialogue, there's 3 embedding values that are extracted from the memory and are simply added together. And knowledge is also represented in this kind of triple and then adding together method. However, we believe that the elements in a dialogue triple and the elements in a knowledge triple might be different, and using a simple summation relies on the assumption that training the memory can overcome this difference between the two. As seen from the previous example, the original paper uses a simple summation of the 3 embeddings, and this was because it's the most simple method of combining 3 embedding values of the same size. And since addition is simple, this is relatively cheap in terms of computation. We are instead planning to use a concatenation of the 3 embeddings, and then using a feed-forward neural network to return to the original dimensionality. Of course, this increases the complexity of the model, but we believe that simple summation might pollute the embedding values and then cause a loss of information. And there's no clear answer on which of these 2 techniques are superior, so we find it valuable to modify the model and to try to use concatenation to experiment. So instead of using a summation, we are trying to make a concatenation of the elements and then using a feed-forward neural network to create a new embedding. Another method of improvement is to change how temporal information is represented within the model. In the same example as before, the words uttered here by the user are put into a triple form, but as you can see in the example, there is information of the turn number, but there's no information on when the word was spoken within the turn. And we believe that the order of words within a turn is very important to correctly understand the meaning. So to include such information, we are using a technique called positional encoding to the embedding output of the encoder, as you can see in the right bottom figure. This method injects positional information to each of the vectors. The frequency depends on the vector's dimension, and it uses sine and cosine on even and odd positions respectively. This technique allows our encoded vector representation to have unique temporal information within its values. In this section, I'll talk about how we plan to progress further. Okay, so after our progress update, we will further consider other methods of improvement and then use those to modify our replication. In the next week, we will continue modifying the replication and then make a performance check around this time. In the final weeks, we will analyze the results and then start working our final report. In the last week, we will finish our project and then report what we have. Here's how we will split the roles. Wijun and Cheolun will be in charge of replicating the model. I and Jonghyuk will be pre-processing the dataset. All of the members will be checking the performance of the replicated model and analyzing the results and searching for ways to improve further.